So do you see my slide?
Yes, very well.
Okay, shall I just start?
Yeah, please start.
Okay, thank you. So my title is Searching Beyond the Standard Model. Of course, Jose has just been talking to you about an area of particle physics where we've already seen beyond the standard model, but I'm going to be looking for possible other signatures of new physics. And the motto of this talk is given here. The direct method may be used, but indirect methods will be needed in order to secure victory. Who can exhaust the possibilities of their combination? And as you probably know, these quotations are taken from Sun Tzu, The Art of War, although I'm going to be applying his advice in a somewhat different way. So where are we? So here are the particles, matter particles appearing in the standard model with their SU3 cross SU2 cross U1 quantum numbers, which of course extremely well established. Correspondingly, we have this Lagrangian here. So the gauge interactions and the interactions of the matter fermions have been tested extremely well with a precision better than 0.1% already before the LHC got started. And in the two lower lines, we've got the Higgs, its couplings to fermions, to Yukawa interactions, the Higgs potential. And this, of course, is the area of the standard model, which is now being tested with increasing precision by the LHC. The question then is, what lies beyond these particles, these interactions in the standard model? So here you see a plot of many of the LHC measurements that have been accumulated over the last decade. And the good news, or is it the bad news, is that all these measurements agree very well with the standard model. So the different colored marks here correspond to measurements by CMS at different center of mass energies, and the sort of gray bars correspond to the theoretical prediction, and there's no significant discrepancy. And this remark applies in particular to processes involving the production of the Higgs boson, which is shown over there on the right-hand side. And as you can see, there are an increasing number of processes where Higgs production has been not just observed, but measured in some cases quite accurately. So back in 2012, when the Higgs boson was discovered, I think it was a perfectly legitimate question whether the particle that had been found in this search for the Higgs boson was in fact the Higgs boson or some imposter. So I like to compare the situation to completing a jigsaw puzzle. And the question was, has LHC found the missing piece? Is it the right shape? Is it the right size to correspond to the standard model prediction? So what do we know now? Well, its mass has been measured really quite precisely by the Atlas and CMS experiments. Already in run one of the LHC, there was a measurement at the precision of 2 per mil. Subsequently, measurements at run 2 of the LHC by Atlas and CMS have further improved the precision, and overall, the Higgs boson mass is now known with an accuracy of about 0.1%. You may say, well, that's all very well, but why should I care? Well, I think you should care because the mass of the Higgs boson and the mass of the top quark are crucial for the stability of the electroweak vacuum. And this is one of the problems which is raised by the successful search for and measurements of the Higgs boson. The more we look at the Higgs, the more it walks and quacks, just the way it should in the standard model. So for example, one key prediction of the standard model was that the couplings of the Higgs to other particles should scale proportional to their masses, and that the overall coupling scale should be identified with the Electroweak vacuum expectation value V of 247 GeV. Well, that prediction of the standard model seems to work very well. So here is another plot from CMS. And what you see here are the measurements of the couplings of the Higgs boson to the top quark, the W, the Z, the bottom, the tau, and just a recent measurement, the coupling to the mu, which all agree very well with the standard model prediction, which is shown here as the dashed line. So, as I commented, this particle walks and quacks like a Higgs boson, and I think Peter Higgs can continue to be extremely happy about it. However, I think basically everything about the Higgs boson is puzzling. And here I've picked out of the standard model Lagrangian the terms which involve the Higgs. So we've got the Yukawa couplings of the Higgs to matter fermions. We've got the quadratic h squared term, which has a quote unquote wrong sign. We've got the quartic Higgs potential term, and we've got a constant term, vacuum energy or dark energy, if you prefer. So immediately we have a problem with the pattern of Yukawa couplings, which Jose has just been discussing in his talk. And this is related to the Flavour problem that he spent quite a bit of time discussing. The second term, the mu squared term, there's an issue here with its magnitude. And this is related to what are called the naturalness and hierarchy problems. Then we come to the issue of the magnitude of the quartic coupling lambda. And this is again related to the stability of the electroweak vacuum. And finally, we have the term V0, which can be identified as a cosmological constant related to the cosmological dark energy. And there's also the issue whether, in addition to these expected, and in many cases known, interactions of the Higgs boson, there might be additional higher dimensional interactions. So basically, the Higgs is still terra incognita, posing many problems. So here's a slide where I illustrate the possible accuracies of future Higgs measurements. So this is taken from the CDR for the FCC project being proposed in Europe. They're very similar results for the CEPC and SPPC projects being proposed in China. So along the horizontal axis here, you see the couplings of the Higgs to various different pairs of standard model particles, including also the invisible decay mode, which was talked about by Kun Chung an hour or so ago. And you see the accuracy that can be reached in the future with high luminosity LHC running and the various different FCC options. So what you see is that FCC-EE, or equivalently CEPC, can give you extremely high precision in measurements. And of course, FCC-HH or SPPC will give us extremely high statistics. The comment that I would make on this is that we're going to need to reduce the theoretical uncertainties in order to match the experimental errors, and in order to extract the maximum juice of interpretation of possible physics beyond the standard model, we theorists have to work very hard. So yesterday, Alessandro Bonanno mentioned all the interesting calculations that are needed in order to fully interpret gravitational wave observations. So here I've taken just a few examples of what would need to be calculated in order to extract the maximum information from Z goes to BB bar measurements at CEPC or FCC EE. So this process, if you want to match the prospective experimental errors, should be calculated to three-loop order, which is going to involve calculating not just dozens, not just hundreds, not just thousands, not just tens of thousands, but over 100,000 individual diagrams. So there's plenty of work for us theorists. There's no danger that we're going to be out of a job. So in the list of Higgs couplings that I showed previously, there was one missing, which is the Triple-Higgs coupling. And we see on the right here a plot from Atlas, which shows the current accuracy with which the Triple-Higgs coupling is measured. So there's some sensitivity from both single and double Higgs production, but as you can see, the overall accuracy is not good at all. It's at the level of several times the standard model prediction. And measuring this self-coupling of the Higgs is crucial, again, for such issues as the stability of the Electroweak vacuum. And it's also related to the possibility of a first-order phase transition in the early universe, which would be interesting, for example, for baryogenesis, but would also be interesting for gravitational wave experiments, as I will discuss later on. So what will future experiments, collider experiments, be able to do in terms of measuring the Triple-Higgs coupling? So there is some sensitivity from E+ E- collisions, FCC EE is illustrated here on the right-hand side, and essentially equivalently CEPC. And it'll be possible to measure the Triple-Higgs coupling with an accuracy of something like 30%, depending on the assumptions that you make. So this is a compilation from Diboson et al. That shows you the prospective sensitivities to the Triple-Higgs coupling in various different projects, starting off with a high luminosity LHC at the top, which might give you, say, something like a 50% measurement, FCC EE or CEPC, which we just saw, and going down is also CEPC lower down there. So there are some prospects for measuring the Triple-Higgs coupling, but an accurate measurement is quite some way in the future, and I'll return to that point later on. So I've been spending a bit of time discussing the Higgs boson and measurements of its properties. But of course, what we would really like to see at the LHC and future colliders is some new particles beyond the standard model. And of course, there have been lots of searches. Searches for supersymmetry, none seen yet. Searches for other things like models with extra dimensions that Jose Valle discussed in the previous talk. Nothing there either. So there's a lot of discussion at the moment as maybe there's some unexplored corners of the parameter spaces of such models as supersymmetry. Maybe we should be looking for novel signatures like the long-lived particles that was discussed by Dr. Chung just an hour or so ago. Or maybe we're going to have to reconcile ourselves in the upcoming collider experiments to looking indirectly for signatures of beyond the standard model physics, following the advice of Sun Tzu. So now I'd like to spend a bit of time discussing effective field theories as a tool for looking indirectly at physics beyond the standard model. So I'd like to remind you that effective field theories have a long and glorious history. So cast your mind back to the 1930s. So at that time, we had what I call here the standard model of quantum electrodynamics, which of course had dimension 4 interactions. But Fermi said, well, look, if we want to understand the weak interaction, we should consider an effective 4-fermion theory, dimension 6. And then, of course, there's a lot of discussion about what the form of those dimension 6 operators might be: scalar, pseudoscalar, vector, axial, tensor. And it was also suggested that the dimension 6 interaction might be generated by the exchanges of massive particles. So then in the 1950s, after a little bit of experimental to and fro, it was established that the weak interaction has a V minus A form. That, of course, suggested to people that the massive particles being exchanged might be vector bosons. The issue then was, how do you write down a consistent theory of massive vector bosons? And that led us to gauge theory and spontaneous symmetry breaking. Meanwhile, in the strong interactions, Yukawa proposed his meson theory. What were the mesons? Well, there were pions, those were the lightest ones, but already they were heavier than the characteristic nuclear physics scale. Then people looked at the dynamics of those pions, and they realized that they had very special chiral properties. And that was actually a crucial clue towards QCD as a theory of the strong interactions. So effective field theories actually had very important roles in the establishment of the standard model, both in the weak sector and in the strong sector. So, can we follow the same road again? One possible way to look for beyond the standard model physics is what is called the standard model effective field theory. So you write down higher dimensional operators composed of standard model fields, starting off with dimension 6, if you're interested in collider physics. The operators that are legal are those that are constrained by SU2 cross U1 symmetry, assuming the conventional representation assignments for standard model particles, which by now have been extremely well established. Then, once you've written down your Lagrangian, you try to constrain the coefficients with the data available from collider physics in particular, in the top Electroweak, Higgs, and Diboson sectors. And if you find a non-zero coefficient, that could indicate what is the nature of the physics beyond the standard model, and maybe give you some hints about the masses, spins, and quantum numbers of new particles. And if you find, for example, that there are derivative interactions, that might be characteristic of some new strong dynamics. So that's the basic idea. So now I want to spend a little bit of time discussing a global fit to the standard model effective field theory using top Higgs, Diboson, and Electroweak data that Maeve Madigan, Ken Mimasu, Veronica Sands, and Tivong Yu and I put out just a few days ago. So here you see, in a somewhat simplified form, some of the operator coefficients that appear in a global fit. And you see various different boxes which show you how different sectors of measurements at the LHC contribute to constraining different combinations of operators. And as you can see, there's a considerable overlap between the sensitivities that you get from different classes of measurements, Higgs, top, Electroweak, and so on. So in our paper, we didn't just do an analysis of the operator coefficients. We also looked at constraints they impose on certain beyond the standard model scenarios at the tree and loop level. Unfortunately, we didn't find any indications of new physics beyond the standard model, but let me take you through a little bit our analysis. So here's a somewhat more detailed picture of the dimension 6 operators that we analyzed. So some of these involve bosons, some of them involve fermions, some of them appear when you break the SU3 to the 5th symmetry of Flavour, which is a natural thing to do when you're considering top observables, as we do in our global fit. This one here outlined in blue is a derivative interaction between Higgses. If we found that the coefficient for that was significantly non-zero, we might say, well, perhaps that's an indication of some chiral new strong dynamics. And this operator here, an H⁶ interaction, this could generate a cosmological phase transition, as well as generating a deviation of the Triple-Higgs coupling from its standard model value. So what do we find? So on the right-hand side, we've got constraints on the operator coefficients scaled to a new interaction scale 1 TeV in the top panel. In the second panel, we've got a constraint on the scale lambda, assuming various different values of the couplings, whether they're 1, bigger than 1, or smaller than 1. So the top two panels are when we switch on one operator at a time. And the lower panel is when we allow all the operators to be switched on. And for each operator coefficient, we marginalize over the other operators. So those marginalized constraints are typically weaker, but you see that those marginalized constraints are typically already at the level of 1 TeV or so, and the individual constraints, the blue bars in the upper panels, extend to 10 TeV in some cases. So that previous fit was not treating the top couplings any different from the couplings of the lighter quarks. But, maybe they're different. After all, the top quark is much heavier than the other matter fermions. So here again is a similar set of plots. The top half is individual operator coefficients. The lower half is when we allow all the operators to contribute, and for each operator we marginalize over the coefficients of the other operators. Again, we see that there are many constraints at the level of 1 TeV in the marginalized case, or 10 TeV in the individual case. But if you look over on the right-hand side, there are the new operators that come in when you allow top couplings to differ from couplings of the lighter generations. And you see that those couplings are constrained more weakly. So the constraints there hover around a few hundred GeV for a coupling of order 1. If you take the marginalized fit, somewhat stronger, of course, if you take the individual fits. So, depending on your assumptions, the constraints on these operator coefficients can vary between several hundred GeV and more than 10 TeV. Now, one of the other things that we did in our analysis was to look at the correlations between the various different operator coefficients. So you certainly see correlations within sectors. For example, up in the top right-hand side there, we see that operators involving the top are very much correlated amongst themselves. However, there are also significant correlations of the top sector with other sectors. So you can diagonalize that very complicated matrix and see which combinations of operators are most constrained and which combinations are less well constrained. So you basically diagonalize the matrix and analyze the eigenvectors and the eigenvalues. And here you get constraints going all the way from 20 TeV down to something more like 100 GeV, although that operator is a somewhat special case, which is basically decoupled from the others. This, by the way, is what I call the go board plot in deference also to East Asian culture. Generally speaking, as we saw previously, the strongest constraints come from the Electroweak and Higgs sectors, weaker constraints coming from the top sector. Okay, so that was a very sort of generic analysis. What happens if you add to the standard model one new particle? So we analyzed all possible single field additions to the standard model. And the names are here on the vertical axis, and the strength of the constraint on those possible particle masses in TV is shown on the horizontal axis. So you see that constraints again go up beyond 10 TeV in some cases. We find no significant pulls away from the standard model prediction. But basically, any of these beyond the standard model scenarios must have a scale larger than 400 GeV if the coupling is equal to 1. So I mentioned the S word earlier on. I said that experiments at the LHC had looked for supersymmetry, but hadn't found it. And one of the supersymmetric possibilities that's often being considered is the possibility that there might be relatively light stop squawks. Now, supersymmetry has many parameters, and it's often rather difficult to do a scan over all the possible values of those parameters. The standard model effective field theory enables you to establish what are not exactly model-independent constraints, but less model-dependent constraints on the light stop scenario. And here you see that our analysis tells you that stops have to weigh more than about 300 GeV, except in one very special case for the stop 1, stop 2 mixing parameter. We tried something else. So that stop scenario, the stops contribute to 4 different operator coefficients. So there are some simple extensions of the standard model that only contribute to 1 operator. There are others that contribute to more than 1. So what we did was we looked at all possible combinations of 2, 3, 4, and 5 operators in the SMEFT. And we asked, is there any indication for any combination of up to 5 operators of a deviation from the standard model? So if you look at operators that don't involve the top, they fit the standard model very well. Top sector, not so well. And we scratched our heads a little bit as to whether the discrepancy there could be considered significant. I think not. There was one particular LHC measurement, which we're a little bit suspicious of, which is TT bar production close to threshold. I'd be happy to discuss that if people want. Anyway, we don't consider that even this very generic analysis gave any hint of any specific beyond the standard model scenario. So what's going to happen in the future? Well, FCC, CEPC will establish greater sensitivity to those effective field theory coefficients. And this illustrates here the prospective sensitivities that you get for a wide range of operators. Again, I would emphasize the importance of improved theoretical calculations to reduce the uncertainties. So for each of those bars, the dark bar indicates what you lose if you cannot improve the theoretical calculations to the level that I discussed earlier in my talk. So in my remaining time, I want to discuss something which at first sight looks completely different. So you've had various talks at this meeting, in particular by Alessandra Buonanno, about gravitational wave experiments. And as you've heard from her and others, there's a wide range of spectrum of gravitational waves which are now being explored experimentally. So over on the right-hand side, we have LIGO and its possible successor experiments. Then in red, we have LISA, and in the middle of this plot, you have pulsars, which are also very interesting, as I'll discuss in more detail later on. Now, what you also see is that between LIGO and LISA, there is a gap. And this gap is interesting for various different reasons. It could provide us clues as to the formation of supermassive black holes, but it could also be interesting for looking for signatures in the early universe of the electroweak phase transition and also cosmic strings. And this is a gap that I'll be paying a little bit of attention to in the following slides. But there's also a gap between LISA and pulsar timing arrays, but I won't have time to discuss that. So I declare a personal interest. I am a member of a collaboration in the UK called AON, which is planning to construct atom interferometers to probe gravitational waves. We're going to start off fairly modestly with a 10-meter device. Then we hope later on to go up to 100 meters and 1 kilometer. And we also have long-range ambitions to put atom interferometer in space, a project that we call EDGE, which would in many ways complement LISA. So we've already got initial funding from UK funding agency for AON 10, and we hope eventually, if that proves to be successful, to go on to the larger versions of AON. So what are these useful for? So in this talk, I'm going to focus on probing extensions of the standard model. I won't be discussing the astrophysics. So the previous picture illustrated to you how bubbles of new vacuum form and percolate in the early universe following a possible first-order phase transition. So those bubbles grow, they collide, and there's many ways in which they can produce gravitational waves, through collisions of bubbles and through turbulence and sound waves in the plasma. So we're particularly interested in how they can constrain extensions of the standard model. And let me just discuss two examples. One is where you add that dimension 6 h to the 6th interaction, which I commented on earlier on in connection with collider physics. Another one is where you add in an additional U1 gauge boson, Z prime. Now, these have not just gravitational wave signatures, but also collider signatures. And I'm going to try to compare and contrast prospective sensitivities of gravitational wave and collider experiments. So here's an example from an analysis that we did of the h to the 6th model. So in black, you see the prospective gravitational wave signal compared with the sensitivities of LISA and the EDGE experiment that we're proposing. And you can see that those gravitational wave experiments would have a sensitivity to the scale lambda of the h to the 6th interaction, whereas, for example, LIGO would be relatively insensitive. I should mention, by the way, that current collider experiments have absolutely no sensitivity to this h to the 6th interaction. In fact, EDGE and LISA have rather similar sensitivities to this scale parameter lambda if you're asking for detection at a signal to noise ratio of 8 to 10, which is the sort of gold standard for gravitational waves. So now I'm going to compare directly the gravitational wave sensitivity to the collider sensitivity. So as already commented, current LHC data are completely insensitive to a possible h to the 6th interaction. Future colliders would be sensitive via a modification of the Triple-Higgs coupling lambda 3. And as we discussed previously, future collider experiments may be sensitive to variations in lambda 3 at the level of 10, 20, 30, 50%. And that's illustrated here. So there's no collider sensitivity now. So for the time being, gravitational waves have an open field. However, eventually, colliders, high luminosity LHC in the 2030s, FCC EE or CEPC in the 2040s, FCC HH or SPPC in the 2060s maybe, would beat out gravitational waves. But we see here an example where there is a possible complementarity between collider searches and gravitational wave experiments. Let me take another example. This is where you supplement the standard model with a U1 gauge boson. So here, depending on the mass scale associated with this U1 gauge boson, you could have a detection with LIGO or a successive experiment, or AON or EDGE in the mid-frequency band, or LISA. So here are some plots from AON, the 100-meter version on the left, and EDGE on the right-hand side. And you see here that these gravitational wave experiments have prospective sensitivities out to 100 TeV, which is considerably beyond the prospective sensitivities of not just the LHC, but also FCC and SPPC. So now I want to go back and contrast this with the sensitivity to these Z prime models that we have from the LHC now, both directly, well, there's a direct limit of about 3.5 TeV. So that's obviously much less than the prospective sensitivities of collider experiments. Then there is the indirect limit coming from the SMEFT analysis that I discussed earlier on. And these plots indicate that for couplings of order 1, the indirect sensitivity to a Z prime boson is of the order of 1 TeV. And you can find more details in our paper. So this is an example where collider sensitivity will certainly in the future be less than gravitational waves. So I just want to finish by discussing pulsar timing arrays. So you heard about the prospective sensitivities of these two gravitational waves in talks yesterday. I just want to focus on this recent paper by the NANOGrav collaboration. So they observed 47 pulsars over 12.5 years, and they may have found something. So to quote the NANOGrav paper, they say they find strong evidence for a stochastic common spectrum processing. Well, what that means is that they may be seeing a signal, although they cannot decompose it into dipole or the quadrupole effect that you would expect from gravitational waves. Now, on the right-hand side, you see the results of their fit to the amplitude of the signal and the power law of the signal. Now, the default, quote unquote, standard model for such a pulsar timing array signal would be mergers of supermassive black holes. However, as a particle theorist, I feel entitled to dream about alternative possibilities. So one possibility that I discussed with Marek Levitsky is that they're probing cosmic strings. So people have analyzed string configurations in the early universe. Every once in a while, those strings overlap, they break out loops, and those loops radiate gravitational waves. And here's a picture of a simulation of a cosmic string network by the Cambridge Cosmology group. So it turns out that cosmological string interpretation in the NANOGrav data actually fits the data, dare I say it, a bit better than the quote-unquote standard model of supermassive black holes. So the supermassive black holes would make a prediction corresponding to that vertical gray line, whereas cosmic string interpretation predicts something along that rainbow-colored line, which cuts through the 1 sigma NANOGrav preferred region. And that would correspond to a cosmic string tension of the order of few 10 to the minus 11 to 10 to the minus 10. And if that were to be correct, then those cosmic strings would show up not just in pulsar timing arrays, but in many other gravitational wave experiments as well. So I've already talked about LISA, I've talked about EDGE and AEON. LIGO looks like it might not be quite sensitive. The Tianqin project being discussed in China could also detect these cosmic strings. So let's see whether this hint turns out to have some reality. Okay, so that brings me to the end of what I wanted to say. So let me go back to the image that I had on my first slide. So we're still looking for physics beyond the standard model. Maybe in some cases we see some hints on the distant horizon. Maybe those are real, maybe those are mirages. Only time will tell. Now you might ask yourself, why am I, why are you so confident that there is physics beyond the standard model? So I would like to give you some motivation provided by James Bond, of course, with some modifications. I modify the leading characters. I modify the title of his movie. The standard model is not enough. And I just list 007 reasons for saying there must be physics beyond the standard model. Empty space is unstable according to standard model calculations. Standard model does not explain dark matter. Standard model leaves open the Flavour problem. As we've heard from Jose, the masses and mixing of neutrinos take us beyond the standard model. There's a naturalness or hierarchy problem. We'd like to have a cosmological inflation model. We'd like to make a quantum theory of gravity. So I have absolutely no doubt that there must be something beyond the standard model, and let's keep searching for it. Thank you.
Well, thank you, John, for the very illuminating talk. So we come to the question time. Maybe we can also ask, first ask online people, are there some questions I want to ask? Well, if no, then we come to the local guys. Any question for John? Oh, you have one.
Yeah. Thank you for nice talk. Just curious about, you mentioned about the gravitational wave. So I just wonder, even we have some signal from gravitational wave, do we still need to get back to collider to confirm this signal? Thank you.
I think so, because for any imaginable period of time, certainly for the period of time that I'm going to be interested, maybe even the period of time for which you will be interested, I think the signatures of gravitational waves will be ambiguous. And it will be necessary to cross-check whatever we may learn from gravitational waves with other areas of physics, in particular collider physics. And I must say that would be just a fantastic confirmation of the unification of physics if we could link together collider experiments in the laboratory with observations of the universe.
Well, okay, so let's spin that. I have some questions to ask.
Yeah, thanks for the nice talk. I'm also want to ask something about this gravitational wave story. So you were talking about ION, and you said you got some funding, but I was wondering, is it like still R&D, or will you get some results out of the first stage of ION?
Okay, so the initial funding that we've got will enable us to establish various strontium labs around the UK and do the preparatory work to install the 10-meter device, which would go into the Oxford Physics Department. That device would be sensitive, realistically, not to gravitational waves, but it would have some capabilities for ultralight dark matter, which I'd be happy to discuss, but I didn't have time to talk about. A similar level of investment would get you into the gravitational wave business. And we've been investigating various places in the UK to site such a 100-meter device, or it could be located at CERN. And I should mention that in parallel, there is a project in the US called MAGIS, which is also aiming at the construction of a 100-meter device, which would have similar capabilities. Ideally, of course, one would like more than one device, like one has LIGO and Virgo. And that's something that we would hope to reach, let's say, 5 to 8 years' time. That would be the realistic hope.
Okay, so next, Chongqing Zhu.
Thank you, John, for a very nice talk. As you are always inspirational, I would like to ask your opinion about which one of these 7 items, or even maybe the ... one, you think will be more likely or most likely that we can find something?
Well,
let's give you a bet.
So Jose and his friends with number 4 on the list, they're lucky, they've already found it. As to the others, at various times in my research career, I focused on different problems. I'd have to say that right now I would be most optimistic about making progress on the dark matter issue, just because there's so many dark matter candidates which look to me to be plausible and within reach or almost within reach of various different experiments. Collider experiments, the Axion experiments that also Jose touched upon, also these ultralight dark matter search experiments that you can do with, for example, atom interferometers. So I think there's so many ways that we can attach the dark matter problem that I'm still quite hopeful, if not optimistic, that we may crack that one relatively soon.
Okay, John, I have a question. I was surprised in supersymmetry doesn't show up today in your slides. So no more supersymmetry?
Well, supersymmetry actually did show up, right? It showed up when I said that we didn't find it yet in collider experiments, although we're still looking. And we specifically did, as part of our SMEFT analysis, a study of the sensitivity to light stops. So yeah, we're certainly still looking for supersymmetry. There are corners of parameter space where we can still search for supersymmetry with the LHC, but it may be that if we're going to find it, we're going to have to look elsewhere, such as a future collider.
Well, okay, so any more questions to John? Well, if not, let's thank John for the wonderful talk. Well, okay, so since I'm the last session chair, usually at the end, you have a lot of things, a lot of people to thank. Well, okay, so I think we first thank all the speakers of this conference, and of course, the people show up online and on site. Without this, we cannot have the meeting. Let's thank all us.
And
of course,
Xiaogan,
yes.
Xiaogan, can I say something?
Yes, please.
Yeah, so just on behalf of all the speakers, I would like to thank you and your colleagues for your kind virtual hospitality. We realize that we're all living through exceptional times, and it's great that you're all able to organize such a wide-ranging virtual meeting. But I think I can speak certainly for Jose and myself, that we really look forward to having a real physical meeting as soon as possible. So anyway, thanks very much.
Yes, I think we have a rain check for you too at some convenient time, and to come when you are allowed to travel. We are allowed to accept the people from outside. I think we have this coordinator there, Tsing Wei. He will pay the bill. Okay. Yeah. So we have Candy. She has organized all the details and get things so well organized that and her team for the other secretaries. Let's give Candy and the secretaries a big hand. Of course, this conference series, the NCTS Annual Theory Meeting. So for this particle, cosmology, and the string was initiated in phase 4. This is phase 4, right? Oh, phase 4. So Changxin too has done a very devoted job and have a lot of creative ideas, including this conference series. Without him, probably we would not have this conference series. Let's thank Changxin for for his very devoted job as a physics division and director of NCTS. So this conference, of course, in a different form, maybe will continue in the next phase. This is the end of this phase. So we have the 6 years. Next phase will move to NTU. So this conference series maybe will incarnate in some other form or continue in some form. Again, we have Chen Wei as one of the representatives. So the bill will be paid by you again. Yeah. Okay. So I think at this moment we can close the conference. Thank you for you all stay here to the end. Yep.